Dear students, in this video, we will see how to solve the Schrodinger wave equation for one-dimensional simple harmonic oscillator and finding out the eigenfunctions and eigenvalues. Any device that interconnects potential energy and kinetic energy repeatedly is an oscillator. Some examples include a simple pendulum, a mass on a spring, and also vibrating molecules. We know that atoms in a molecule execute vibratory motion. So if such a motion obeys Hooke's law, and what is Hooke's law? If the extension or compression is not very large, then the restoring force, that is a force which acts in the opposite direction, is proportional to the displacement x. That is F is equal to minus kx, where k is the force constant. And this model was proposed by Hooke. And if an oscillating particle obeys Hooke's law, then we say it is a harmonic oscillator. Harmonic oscillator is an example of a simple system where potential energy is not constant. Vibrating molecules may be treated as simple harmonic oscillators. If it is a diatomic molecule, we assume that the two atoms are connected by a spring. That is, the atoms are considered as balls and the bond in between is considered as a spring. So that the vibrations of such molecules will be like the oscillations which obeys Hooke's law. The potential energy of such a harmonic oscillator is 0 at its equilibrium position and increases as the spring is stretched or compressed. And the potential energy is given by E equals half kx square, where k is a force constant and x is the displacement. The frequency of oscillation is given by nu equals 1 by 2 pi root of k by m, where m is the mass of the particle. Now here you can see that at the extreme points, that is at minus a and plus a, all the energy is potential energy represented as half k square. At the equilibrium point, that is at x is equal to 0, all the energy is kinetic energy. So the points minus a and plus a are called the classical turning points. So the potential energy at any point should be less than the total energy half k square, because otherwise kinetic energy will be negative, which is not possible. Now let's see the quantum mechanical treatment of one-dimensional harmonic oscillator. That is, how to solve the Schrodinger wave equation and how to find out the eigenfunctions and eigenvalues. The Schrodinger equation for one-dimensional simple harmonic oscillator is obtained as follows. We can write the Schrodinger equation as h cap psi equals E psi, where h cap is the total energy operator. That is, we can write h cap as a sum of kinetic energy operator and potential energy operator. In the case of a simple harmonic oscillator, the potential energy V is equal to half kx square. And the frequency of oscillation nu equals 1 by 2 pi root of k by m. Therefore, k equals 4 pi square nu square m. Substituting the value of k in V, we get V equals 2 pi square nu square m x square. This is the value of the potential energy operator. The value of kinetic energy operator is given by minus h square by 8 pi square m d square by dx square. Therefore, the Hamiltonian for a harmonic oscillator is given by h cap is equal to minus h square by 8 pi square m d square by dx square plus 2 pi square nu square m x square, where m is the mass, x is the displacement, nu is the frequency of oscillation. The Schrodinger equation h cap psi equals E psi for such a motion may be written as minus h square by 8 pi square m d square xi by dx square plus 2 pi square nu square mx square into xi equals e xi. We can rearrange this equation as d square xi by dx square plus 8 pi square m by h square into e minus 2 pi square mu square mx square into xi equals 0. Let this be equation 1. Now this can also be written as d square xi by dx square plus 8 pi square me by h square minus 16 pi raised to 4 m square nu square by h square into x square the whole into xi equals 0. Let this be equation 2. Now we are going to give a substitution. Let alpha equals 8 pi square me by h square and beta equals 4 pi square nu m by h. So substituting alpha and beta in equation 2, we get d square xi by dx square plus alpha minus beta square x square into xi equals 0. Equation 3. This equation can be solved subject to the following boundary conditions. As x tends to plus or minus infinity, xi tends to 0. In order to apply this boundary condition, we make the following change of variables. Let y equals root beta into x. So we can write x equals y by root beta or dx equals dy by root beta. Also, we can write d square xi by dx square will be equal to beta into d square xi by dy square. So substituting these values in equation 3, we get beta into d square xi by dy square plus alpha minus beta square into, instead of x square, we write y square by beta into xi equals 0. That is, we can also write d square xi by dy square plus alpha by beta minus y square into xi equals 0. We have divided both the terms by beta. So we get d square xi by dy square plus alpha by beta minus y square into xi equals 0. And let this be equation 4. This is a purely algebraic equation. Now we have to find out the solution for this equation. So we are dealing with the quantum mechanical treatment of one-dimensional harmonic oscillator. First we wrote the Schrodinger equation h cap xi equals E xi, where h cap is the Hamiltonian, that is a total inertia operator, and its value is given by minus h square by 8 pi square m d square by dx square plus 2 pi square nu square mx square. And the Schrodinger equation becomes minus h square by 8 pi square m d square xi by dx square plus 2 pi square nu square mx square xi equals E xi. We rearrange the equation and give substitution for alpha and beta. Alpha equals 8 pi square me by h square and beta equals 4 pi square nu m by h. And then we get equation 3, that is d square xi by dx square plus alpha minus beta square x square into xi equals 0. In order to solve this equation, we apply a boundary condition, that is as x tends to plus or minus infinity, xi tends to 0. And we make a change of variable from x to y, that is y equals root beta into x. So x equals y by root beta, dx equals dy by root beta, and d square xi by dx square will be equal to beta into d square xi by dy square. Now substituting these values in equation 3, we get beta into d square xi by dy square plus alpha minus beta square into y square by beta into xi equals 0. If we divide these terms by beta, then we get d square xi by dy square plus alpha by beta minus y square into xi equals 0, which is an algebraic equation. Now we have to find a solution for this equation. What is meant by an asymptotic solution? A solution goes to an asymptotic value if, as the independent value tends to infinity, the dependent variable or its derivative tends to some constant value. For example, the function y equals 2 plus 1 by x. This function tends to asymptotic value of 2 as x tends to infinity. Similarly, here we can obtain an asymptotic solution for very large values of y. So when y is very much greater than alpha by beta, then equation 4 reduces to d square xi by dy square minus y square xi equals 0. The solution of this equation can be shown to be xi equals e raised to plus or minus y square by 2. D square xi by dy square is equal to d square by dy square e raised to plus or minus y square by 2, which is equal to y square e raised to plus or minus y square by 2 plus or minus e raised to plus or minus y square by 2. So this is equal to y square plus or minus 1 e raised to plus or minus y square by 2. For very large values of y square plus or minus 1 approximately equal to y square. So we can write d square xi by dy square equals y square e raised to plus or minus y square by 2, which is equal to y square xi. So thus we can prove that the solution of this equation d square xi by dy square minus y square xi equals 0 is xi equals e raised to plus or minus y square by 2. So here d square xi by dy square is equal to y square xi, or d square xi by dy square minus y square xi equals 0, which is the same as equation 5. We have two solutions. Either xi equals e raised to plus y square by 2 or xi equals e raised to minus y square by 2. Now out of the two solutions, e raised to plus y square by 2 is not acceptable, because in that case xi will rapidly increase tending to infinity as y tends to plus or minus infinity. Therefore, the solution e raised to minus y square by 2, which satisfies the boundary condition, is the one valid for large values of y. Thus, we see that xi equals e raised to minus y square by 2 is an asymptotic solution to equation 4. So this suggests that the general solution of equation 4 contains the factor e raised to minus y square by 2, and we assume that the complete solution of equation 4 is of the form xi equals f of y e raised to minus y square by 2, equation 6. So out of the two solutions, xi equals e raised to plus or minus y square by 2, xi equals e raised to minus y square by 2 satisfies the boundary condition. So the general solution of the equation 4, that is d square xi by dy square plus alpha by beta minus y square into xi equals 0, that is equation 4. So the general solution of this equation will contain the factor e raised to minus y square by 2, and therefore the complete solution of equation 4 will be of the form xi equals f of y e raised to minus y square by 2. f of y can be determined by finding its differential equation. So first we have to do d psi by dy and then d square psi by dy square. D psi by dy is equal to f of y into d by dy of e raised to minus y square by 2 plus e raised to minus y square by 2 into d by dy of f of y. This into minus 2y by 2 e raised to minus y square by 2 plus e raised to minus y square by 2 into df by dy. Now we have to do d square psi by dy square. D square psi by dy square equal to e raised to minus y square by 2 into d square f by dy square minus 2y df by dy plus y square minus 1 into f. Equation 7. Now we have to substitute the value of d square psi by dy square in equation 4. Let me write once more equation 4. D square psi by dy square plus alpha by beta minus y square into psi equals 0. So in equation 4 we have to substitute the value of d square psi by dy square and also psi. And psi is f of y e raised to minus y square by 2. So substituting in equation 4 we get e raised to minus y square by 2 d square f by dy square minus 2y df by dy plus y square minus 1 f. So this is d square psi by dy square plus alpha by beta minus y square into psi, and psi is f of y e raised to minus y square by 2. So this is equal to 0. In both terms e raised to minus y square by 2 is common. So taking e raised to minus y square by 2 outside, we can write e raised to minus y square by 2 d square f by dy square minus 2y df by dy plus y square minus 1 into f. Here alpha by beta minus y square into f. So in two terms f is common. So this can be written as alpha by beta minus 1. Y square and y square will get cancelled. So alpha by beta minus 1 into f equals 0. Here the exponential factor cannot be 0. It should always be positive. Therefore, d square f by dy square minus 2y df by dy plus alpha by beta minus 1 into f equals 0. Equation 8. This is a differential equation for the function f of y, and it is known as Hermite's differential equation. This is an equation well known in mathematics. It has been studied and solved by Hermite, a mathematician, and is known as Hermite's equation. Now this function can be solved by polynomial method by assuming that the function f can be expanded as a power series in y. So equation 8, which is known as the Hermite's differential equation, can be solved by polynomial method. That is, we are going to expand f as a power series in y. That is, f equals a0 plus a1y plus a2y square plus a3y cube plus a4y raised to 4 plus etc. Let this be equation A. Now find df by dy. df by dy can be written as a1 plus 2a2y plus 3a3y square plus 4a4y cube plus etc. Let this be equation B. Now find d square f by dy square. D square f by dy square is equal to 1 into 2 a2y plus 2 into 3 a3y plus 3 into 4 a4y square plus etc. Let this be equation C. Now we have to substitute a, b and c in equation 8. Substituting in equation 8, we get 1 into 2 a2 plus 2 into 3 a3y plus 3 into 4 a4 y square plus etc. minus the next term is minus 2y into df by dy. So we have to multiply 2y into equation B, df by dy. So we can write minus 2 into 1 into a1y plus 2 into 2 into a2y square plus 2 into 3 a3y cube plus etc. And the last term is alpha by beta minus 1 into a0 plus alpha by beta minus 1 into a1y plus alpha by beta minus 1 into a2y square plus etc. equals 0. Now this equation can be satisfied only if the coefficient of each power of y is 0. For example, if we take the coefficient of y square, 3 into 4 into a4 plus 2 into 2 into a2, and also alpha by beta minus 1 into a2. The sum of all these terms should be equal to 0. Similarly, for each power of y, that is for y cube, y square, y, etc. So for y raised to 0 term, y raised to 0 means 1. So pick out the terms in which there is no y. So for y raised to 0, the coefficient is the first one. Here we have 1 into 2 into a2. So this term. Now the another term that does not contain y is alpha by beta minus 1 into a0. Write down that term plus alpha by beta minus 1 into a0 equals 0. Now for y raised to 1, pick out the coefficients of the y term. So here we have 2 into 3 into a3. And here 2 into 1 into a1. And last terms alpha by beta minus 1 into a1. 2 into 3 into a3 plus alpha by beta minus 1 minus 2 into 1 into a1 equals 0. Similarly for y raised to 2, picking out the coefficients of y square. So we have 3 into 4 into a4 plus alpha by beta minus 1 minus 2 into 2 into a2 equals 0. So for y raised to 1, we have 2 into 3 a3 plus alpha by beta minus 1 minus 2 into 1 into a1. For y square, 3 into 4 a4 plus alpha by beta minus 1 minus 2 into 2 a2. So for y raised to 3, it will be like 4 into 5 into a5 plus alpha by beta minus 1 minus 2 into 3 into a3 equals 0. So if we go on like this, we get for y raised to k, it will be k plus 1 into k plus 2 into a k plus 2 plus alpha by beta minus 1 minus 2 into k into ak equals 0. Therefore, we can write ak plus 2 equals minus alpha by beta minus 1 minus 2k into ak divided by k plus 1 into k plus 2, where k is an integer. And this equation is known as recursion formula. It permits the calculation of the coefficient ak plus 2 of the term y raised to k plus 2 in terms of the coefficient ak of y raised to k. Recursion formula is a standard result of series solution method of solving differential equations. It gives one coefficient in the series expansion of f in terms of a previous coefficient. The above equation is called a two-term recursion formula. Harmonic oscillator wave function is given by xi of y equals f of y e raised to minus y square by 2. The power series will consist of infinite number of terms, and the function f of y will tend to infinity as y tends to infinity. That is, the behavior of power series for large values of y is unacceptable. So to avoid this difficulty, we have to restrict the number of terms in the series. That is, terminate the series after certain number of terms so that we have a polynomial solution instead of power series. And this is possible if for a certain value of k, say n, the numerator in equation 9 vanishes. That is, when alpha by beta minus 1 minus 2k equals, if k equals n, alpha by beta minus 1 minus 2n equals 0. So we are limiting the series only up to n terms, and after that equation 9 vanishes, or we can write alpha by beta minus 1 minus 2n equals 0, or we can write alpha by beta equals 2n plus 1, or alpha equals beta into 2n plus 1, where n equals 0, 1, 2, 3, etc. The resulting series with a finite number of terms is a polynomial called Hermite polynomial, denoted as hn of y. The Hermite polynomials are defined by the generating function hn of y equals minus 1 raised to n e raised to y square d raised to n by dy raised to n of e raised to minus y square. So hn of y is known as the Hermite polynomial, which we obtained from the recursion formula. Therefore, the harmonic oscillator wave function now becomes xi n of y equals hn of y e raised to minus y square by 2, where hn of y is known as the Hermite polynomial, and its value is given by minus 1 raised to n e raised to y square d raised to n by dy raised to n of e raised to minus y square. So this is the eigen function of one-dimensional harmonic oscillator. Now we have to find out the energy eigenvalues of harmonic oscillator. So from the recursion formula we got alpha equals beta into 2n plus 1. And we had substituted for alpha and beta in the introduction steps. That is, alpha equals 8 pi square m e by h square, and beta equals 4 pi square m nu by h. Substituting alpha and beta in this equation, we get 8 pi square me by h square equals 4 pi square m nu by h into 2n plus 1. Therefore, from this we get E, the energy, equals 2n plus 1 by 2 into h nu. That is, we can write En equals n plus half into h nu, where n equals 0, 1, 2, 3, etc. En equals n plus half into h nu, where h is the Planck's constant, nu is the frequency of oscillation. And this represents the eigenvalue, energy eigenvalue of one-dimensional harmonic oscillator. And nu equals 1 by 2 pi root of k by m. The energy of the harmonic oscillator, that is En, is known as the vibrational energy, and n is the vibrational quantum number. So this shows that the energy of the harmonic oscillator is quantized, contrary to the classical view. And this result emerges from the solution of the Schrodinger equation. So we have subscripted E with n to indicate that there is a set of quantized energy. And these energies are determined by the parameter n, which is called the vibrational quantum number of the oscillator. Now when n equals 0, then we get E0 equals half h nu, and this is called the 0-point energy of the system. For n equals 1, E1 equals 3 by 2 h nu, n equals 2, E2 equals 5 by 2 h nu, etc. Here you can see as n increases by unity, the energy increases by h nu, so that the energy levels are equally spaced. So we have obtained the harmonic oscillator eigen function, that is the wave function, as xi n of y equals hn of y e raised to minus y square by 2, where hn is the Hermite polynomial, and the energy eigenvalue is given by En equals n plus half into h nu, where n is the vibrational quantum number, h is the Planck's constant, and nu is the frequency of oscillation. E is known as the vibrational energy. Now we have to find the normalization constant. It can be determined from the condition that integral minus infinity to plus infinity sin of x square dx equals 1. So please remember, we had made the change of variables and expressed xi in terms of y, that is y equals root beta into x, and also dx equals dy by root beta. So expressing xi in terms of y, the normalization condition can be written as integral minus infinity to plus infinity x n of y square dx equals 1. That is integral minus infinity to plus infinity n, that is the normalization constant, into hn function of y e raised to minus y square by 2, the whole square. X is the wave function, so x n of y square means n h e raised to minus y square by 2, the whole square, into, we have dx here, so instead of dx write dy by root beta. So this is equal to 1. Here n and root beta are constants, so here we have n square and root beta. So taking out of the integral, we can write n square by root beta into integral minus infinity to plus infinity hn square function of y into e raised to minus y square. Here e raised to minus y square by 2 the whole square. So that is e raised to minus y square into dy equals 1. Now evaluation of this integral will give the result n square by root beta into 2 raised to n into n factorial into root pi equal to 1. That is the value of this integral. Integral minus infinity to plus infinity x square e raised to minus y square dy. And that is 2 raised to n factorial root pi. So this equal to 1. So from this we can find out the value of the normalization constant. That is n square equals root beta by 2 raised to n into n factorial into root pi. Therefore, we can write the normalization constant nn equals root beta by 2 raised to n factorial into root pi the whole raised to 1 by 2. Or this can also be written as beta raised to 1 by 2 by 2 raised to n factorial pi raised to 1 by 2 the whole raised to 1 by 2. So this is the value of the normalization constant. Therefore, xi n of y equals nn hn of y e raised to minus y square by 2. And n is the normalization constant and its values given as root beta by 2 raised to n factorial root pi the whole raised to 1 by 2. So this can also be written as xi n of, instead of y, we can write root beta into x. If we have to write in terms of x, root beta x, so that is equal to the value of n, root beta by 2 raised to n factorial root pi the whole raised to 1 by 2, hn of root beta x e raised to minus beta x square by 2. Y is root beta into x. So y square by 2 is beta x square by 2. So this is the eigen function of one-dimensional simple harmonic oscillator, and the eigen value is given by En equals n plus half h nu.